Welcome back to Differential Calculus. I'm your tutor Ryan, and this is a continuation of the Derivation series of Trigonometrics, and we're in part 7b now. So here's where we left off. We're trying to find the limit as h approaches 0 of sine h over h, so let's get started on that. First off, let me explain the diagram to the right side of the screen. We have a circle of radius 1, center is A, first location it touches is at B, and the second location it touches, the edge of the circle, is at Z. We have the outside of the triangle, which is C, the point where the tangent to the circle at Z and B touch, that's Y, and the point directly below Z along the line AB, X. Hopefully you can understand this circle, and as we go through you'll see how I'm going to use the circle, the triangle, and the other line segments within there to find the limit as h approaches 0 of sine h over h. Alright, so from the diagram we can see that xz is equal to az sine theta, but az is equal to 1 since the circle's radius is 1, so xz is equal to sine theta. From here we have xz is less than the magnitude of bz, which is less than the magnitude of arc bz. Now, arc BZ is just the outer rim of the circle squeezed between B and Z. Keep in mind that the value of sine theta is less than the value of theta in general cases. Dividing both sides through by theta, we get sine theta over theta is less than theta over theta, which is equal to 1. So we have sine theta over theta is less than 1. Alright, so from the diagram we can see that the length of BZ is less than the sum of the lengths of BY plus YZ. Thus, theta is equal to arc BZ, which is less than the length of BY and YZ together. So from this we can infer that theta is also less than BY plus YC, and BY plus YC is the line segment BC, and that's equal to AB tan theta. And now, theta, therefore, is less than AB tan theta, but AB is the radius of the circle, and that's 1, so theta is less than tan theta. We also know that tan theta is equal to sine theta over cos theta. Rearranging this, we get cos theta is less than sine theta over theta, and from what we can see in the yellow box on the left, sine theta over theta is less than 1. So, this looks a little familiar from a previous video, and it's time to use the squeeze theorem. So, using the squeeze theorem, the above reads, the limit as theta approaches 0 of cos theta is less than the limit as theta approaches 0 of sine theta over theta, which is less than the limit as theta approaches 0 of 1. Well, we know the limit as theta approaches 0 of something that's a constant is just itself. And we know that the limit as theta approaches 0 of cos theta is 1 as well, because cos at 0 is equal to 1. So, via the squeeze theorem, the limit as theta approaches 0 of sine theta over theta must be 1, because it's squeezed between the limits on the left and the right, which are 1. So there you have it. The limit as h approaches 0 of sine h over h is equal to 1. Alright, let's go back to the original unfinished derivative and fill in the limits that we now know in order to find the derivative of sine of x. So now that we know that the limit as h approaches 0 of cos h minus 1 over h is to be 0, and the limit as h approaches 0 of sine h over h is equal to 1, we can plug that into the original equation, and we're going to get y prime is equal to sine of x times 0 plus cos of x times 1. So we're left with y prime is equal to cos of x. So there you have it. We have proven via the definition of a derivative that the derivative of sine of x is equal to cos of x. That's it. That's all for this video. Questions 2 and up will be in later parts. Thank you for watching.